All right, so these are all the different kinds of tolerances, and we know this is a limits tolerance right here. Let me show you this with this highlighter. Limits tolerance right here, and this is plus minus tolerance, and it is an equal plus minus tolerance. Equal bilateral. It's one that varies in both directions from the same dimension. So there are equal and unequal bilateral tolerances. This is an unequal bilateral tolerance. It's different in the high than the low, or the plus and the minus. An equal bilateral is the same above and below. A unilateral tolerance is the one that goes from 0. So like we saw that diameter of 2 millimeters plus 0.5 minus 9. We don't put a minus, we don't put any dots, we just put a 0. This is my worst case, and that's what I want to see when I'm trying bits or something's very particular to me. So that's called a unilateral. All the tolerance goes in one way. It can only get bigger. Equal bilateral is the same above and below. We talked about that. And we know what a nominal dimension is. It's not always right in the middle. So do you remember in 1433 we had a keyway that had a 0.1243 to 0.1255 dimension. How do you model something like that? So what I told people to do is to find the mean or the middle number. And that would give it a plus minus, right? But that's not always what we're going to have. We're not always going to have that nominal number. We may have something like this. We might have this. How are you going to model that one? A lot of times we're going to go in the middle again, right? Even if it has a deviation tolerance. What really comes around is when we evaluate the parts at the worst case. What is the worst case, the high or the low value? Largest pin, the smallest hole. All right. All limits are absolute. That means when you see a 0.02, it is assumed to have all zeros after it. So we're not rounding something around, right? Basic dimension is basically perfect. If you can remember, theoretically exact, basically perfect. That's the dimension with a box around it. So this is where we can use continuous dimensions. You remember in architecture, they go from outside wall to window to window to window to door to window. It's just like if I had a tolerance on all that, it's called tolerance accrual. I'd have this one to this one to this one to this one, and I'd have a bunch of tolerance after the middle. However, when things are basic, that is absolutely perfect value, so tolerances do not apply. That is gauge makers' tolerances. Tool makers, you know, the gauges that measure it, they're extremely accurate. So that's why we can have continuous dimensions like that. We don't have tolerances adding and adding and adding to make a huge tolerance at the end. Basic dimensions are for gauge information, the position, or the size. It's the true size or perfect size. Uses of basic dimensions. Basic perfect location, size, orientation, which means angle, or true profile. What is a profile? Remember Raising Arizona? I love that movie. You ever seen it? With Nicolas Cage, you haven't seen that?
I've seen it.
That's such a funny movie. And Sally, what was her name? It wasn't Sally Field, was it? Anyway, funniest movie. So she's a cop and he's getting thrown in jail, and they say turn to the left, turn to the left. This is the profile of your face that they want because it's very unique. The profile of something is a side shape. What it's going to look like. If you took something and you thought about it, this would have a profile in this direction, it would have a profile in this direction, and maybe in this direction. And a lot of times whenever I take something and I'm going to reverse engineer something or draw something that I need to make something fit, I will have at least an X, Y, and Z direction profile. Then I'll start making them all fit together. All right, so profile means just that. It could be the profile of a 3D surface or the profile of a line like the outside shape of a car, or the profile turned to the left of my face. It can also, basic dimensions are used for gauge features and datum targets. Now, I don't know if you guys have ever talked about that, but datum targets are a group of pins. Let's say I have to sit this upright like this and measure from something. I might have to have 3 pins to hold that steady. Where these pins are located would be located by basic dimensions. And then with a basic, with the size, so this is datum A, datum A1, A2, and A3. This is a datum to hold it in one direction. So we'll look at datum targets. They can be specified with an X for a pointed pin, a round certain size for a flathead pin, just whatever it needs to hold that in 3 directions to get dimensions off something that you couldn't otherwise, like a basketball. All right, let me see. Title block and general tolerances do not apply to basic dimensions, and that's why we can have continuous dimensions like this right here and get away with it, because the tolerances do not apply. We have to look for the feature control frame that tells us what the tolerance is, and that's why we put this on here. It says, hey, look somewhere else. Okay, on this sheet, now that looks like a nightmare of a drawing, but it's really not if you break it down little by little. Geometric tolerances are used on basic dimensions that specify datum targets. This, all right, everybody, check it out. Here it is. I told you about datum targets. Everybody heads up, look up here. We have 3 flathead pins. They're hatched and have a phantom line on the outside. This is datum A1, A2, and A3. This is the diameter of the pin. It's flat because I see a circular flat face. These would be pointed pins holding this in this direction, and 2 more pins holding it in this side. If you see something like this, it might be the side or the tangency of a pin, just for it to sit up against so it can't move. Then we would use basic dimensions to locate the datum targets to the datum. So you see basic dimensions locating that because it has to be inspection tolerances, tool makers tolerances, not our tolerances off the drawing. And we can look at datum targets more if you guys would like to. Unambiguous, grammatically correct statements for drawing notes. Always in present tense. You don't tell them that, you might want to, you tell them the text will be. You tell them exactly what you want it to be. You don't tell them it was. It's always in present tense. Now let's talk about flag notes and local notes and general notes. General notes we see right here in this drawing. These are general notes, right here. And we're used to that. At the very minimum, we need a material and we need the ASME net standard. Now, every company can follow a different standard. They could still be following 1984. They don't have to go to the latest and greatest standard, and I never knew that. I was unfortunate enough to get invited for some reason to a GD&T when the 2009 rolled out. And there was a bunch of inspectors and engineers and people that liked to argue a lot about what things meant. The people at Applied Materials said they are not going to 2009 yet. So whatever they have on their drawing is what you need to follow as far as the standard goes. And there are some changes from 2009 to the last time. All right, so These are general notes. What about flag notes? Have you guys used flag notes in a drawing? Yeah? Okay, flag notes, if you have a flag, it could be, we used to use squares, rectangles around the number. You don't have to have a decimal point after that. If you have a flag note on here, it better be in this drawing. Because I see people just copy and paste from one drawing to another and there's no flag note. And people are looking for it. So, one real common way to use a flag note is for notes, for marking, part number, revision, right? So let's say that I have this part right here, and I'm going to assemble this to another part over here. And I'm going to have the whole assembly, and it's going to have its own part number that's going to be stamped, let's say. You always want to put your part marking where it's going to assemble to something else and get covered up. Because then they can stamp the assembly here. And it's not that part. So if I have my part number right up here, and my assembly over here, well, which one is it? Make sense? On a part drawing, we might have something and you use a phantom line. That's 2 dashes, like a center line. And then point to that and have whatever kind of flag note that you want. And then in that note, you'll tell them exactly, you know, what font, what process, and what height. And then that phantom area, right? Or bag and tag it. If it's too small to be marked, they will bag it and put a tag on that bag, which we all get from Amazon daily. Local notes. When something says both sides. When something says, let's see. Sometimes we have something that says, did you remember optional on this drawing? Do you remember seeing some things that said optional? There's never anything that's optional. Both sides, or we don't say typical anymore. You could say both planes or both surfaces, those kinds of things that are right by the drawing that have something to do with that. Those would be local notes that are local to the area in which you're talking about, and you don't have to have a flag for it. And we'll see some more examples in here. All right, dimensioning and tolerancing of CAD models, and this hits home right here. Along with CAD models, a line of thinking is developed that we don't need to use dimensions or tolerances, that you can just use the 3D model plus or minus 3% of this shape and everything will be okay, right? But everything has tolerances. It's called nominal thinking and it's flawed. The reality is the produced parts, even if produced directly from the model, will have variation because of shrink rate, because of timing, because of processing, right? What about welding things together? Things warp with heat. All right, part variation. Okay, we already talked about it. Rigidity, size, cleanliness, setup, machine tools, feed, speeds, wear, cleanliness, temperature, fixturing, tooling, measuring methods, and heat treating, secondary operations, chemical conversion coding. All right, without dimensions and tolerances, we could not communicate the allowable variation, make engineering calculations. I cannot say without tolerances if my parts are going to work together at their worst case. At nominal, they'd be fine, but nothing is made perfect. Inspect the part to determine the fitness of use. All right, communicating dimensions on CAD models. CAD file elements are now associated with the CAD models. Have you guys ever used this on a drawing? It calls out a model part number on the drawing. There's another standard. It's MIL standard Y14.41. And what you have to do is you have to call out that model. You have to show the X, Y, and Z from the model so that people can orient it. And then you put your GD and T there, and it says go here for the complete product definition. In the future, guys, it's called model-based definition, MBD. and you would have all your tolerances, all your GD&T. Creo makes you put GD&T in the model, and then you show it in the drawing. Everything else is put on the drawing. So we could do that in SolidWorks and Inventor as well. But you're saying all the tolerances and everything should be in the model. Well, they better be in the model. They have to be in your dimensions. Your dimensions have to be 1, 2, or 3 places, and your tolerances will be inside there as information. I'm going to show you how we can set that up. And that's how we get to evaluate the part at the worst case. Anything specific, and this is critical to function, GD&T, critical to function only, dimensions will show up here. All right, everything else comes from the tolerances specified in the model, and you have to specify that spec. Now I do have that spec if you guys would like to look at that and see what that's like, because that's coming. At some point we won't have drawings anymore. It'll all be in the model. So how are we going to deal with that? And I've seen how manufacturing deals with it, but I haven't seen a lot of design with it. So we're finished with that, and we're going to get right to the questions and answers.